All right, let's start over again now and pick up the interaction idea. What we developed is how a given problem maps solutions in the solution space against a problem element in the problem space. Now, what do we mean by interaction? The problem is if we get a lot of things together, we have to be able to see relationships between those. It's complexity. That's the old difficulty. And what we're up against here is the same problem that you always find if you're working with a lot of things. What do you take first? You put them all in order, and then you start at the first one and work your way through, solve the problem, solve another one, solve another one. Pretty soon you've built up a solution which may no longer work for the first one. So we need not to just take things in an ordered list. We need to put clusters of things together that will be together because the solutions in some way have effect upon the various problems. In other words, problems are related not in terms of the intrinsic nature of their own, but in terms of the solutions which they have. Now let's see if we can get some of those ideas down. Let's take interaction. That's where we really are here in our list of things to cover today. And let's say, why do we want to put problem elements together? And the answer is that we need to see problem elements together because they have potential solutions which affect each other. Or I should say affect each problem. In a way which leads to reinforcement or conflict. See, it's interesting if we have problems which are what you say, more than one, maybe 2, 3 problems which are solved by the same solution idea. That's a reinforcement situation. Those problems are in reinforcement because one solution solves more than one problem. We also can find a great deal of interest when we're looking at situations in which conflict surfaces. That's when you've got a solution which solves one problem but makes it difficult to solve another problem. And quite often they'll get put into a solution because good ideas for the problem they were thought about. But then later on we find out that they prohibit the development of solutions to solve another problem. And that's a situation which really should be covered early on. We should be able to get the solutions looked at together because they're in connection with the problems being together. So we want to organize our problems based on these solution things. Let's take a look at how that sets up in our example here. Here's a big problem space now. And a solution space. And we'll put in problem 1 and problem 2. And we'll put all of the ideas that we had. 1A, 1B, 2A, 2B, 2C, 2D. Now 1A and 1B were thought up for problem element 1. So I'll put them in just as we had them before, and the same with the 2A, B, C, and D for problem element 2. And now I'll go one step farther. I'll say that these are pluses because they solve the appropriate problem, or at least contribute to solving it. But now we can do something else. We can take a look at all the solutions against all the problems. And if you do that, you find that there are a couple in there which have some additional interaction, or I shouldn't say it, would have some additional effect on the problems other than the one they were thought of. For example, 2A is a good idea for solving 1. What was 2A? 2A is a back-mounted lantern. And that does the same thing for this flashlight problem as the lantern that we thought of back here as 1A. So it's a good solution. So we can put a plus in here. Actually, an idea thought up for one problem solves another. But look at what happens with 2C when we compare it with 1, problem 1. Then we get a minus, because 2C is a miner's light. And the miner's light, while it works fine for problem element 2, does nothing to help problem element 1. In fact, it even makes it difficult to solve problem element 1, because we really have to get rid of that special focus, small light area. So what you're seeing now is the development of an idea of interaction. And I want to carry that on further by perhaps generalizing the space thing and talking about it a little more in another diagram. So let's get away from the specific a minute and get back to generalities and say that what we're talking about for any problem element now is what we can call nicely a bullseye diagram, really. Here's a problem element. Problem element number 1. And let's say this is the solution space now that we're interested in for this particular problem element. What we've got is 2 regions. The 2 regions have solutions in them. In this region here, we have all the solutions that support resolution of the problem. And in this region out here, we have all the solutions that obstruct resolution of the problem. Now we actually have one more region, and that's everything outside the bullseye. And those I can characterize with the 0 value. And these are all those out here which have no effect on the problem. And that makes good sense. Now we can say for a given problem, I said problem element 1 in this case, there is a solution space. And in that solution space, there are problems of interest. I'm sorry, solutions of interest to our problem. 2 kinds. Ones that solve the problem and one that keep you from solving the problem. The pluses and the minuses. Now there are lots of other solutions around. There are solutions that you thought up for other problem elements, and they don't necessarily have anything to do with this particular problem element 1, and so they're out here in this other zone. Now if we take this idea, a solution space for a given problem, and we take the idea that we can put we can look at 2 problems together, then we can make a composite diagram of the solution spaces for 2 problems and see how that would look. Let's take a look at that. In order to draw it, I have to put the bullseyes together so that they both are tangent up here at this same spot. It gives us a little bit funny diagram, but there's no other way really to draw it. So let's say that over here on the left I've got the big circle of solutions that are of interest to problem element number 1, and over here are the solutions of interest to problem element number 2. Now inside the bullseye, in other words these little circles, both here and here, we have those solutions which are positive, the ones that support resolution of 1 or support resolution of 2. And right here in the center is the region where they're both positive. So I'll put a double indicator here to indicate left and right and positive for both. Now if I move out to this region here, you can see I have a plus, minus. Plus for number 1, minus for number 2. And over here, symmetrically reversed, a minus plus. If I go a little bit further out, I get plus 0 over here and 0 plus over here. And similarly, I can fill all the rest of these out. This is a minus minus. This would be a, let's see, 0 minus, minus 0, and then out here would be 0, 0. And there are 3 possible solution areas or regions for each problem, so 3 times 3 is 9, and I've got all 9 regions. Now look at what we've got. This is what's interesting from this is a diagram of interaction. Here in the center is that region where a solution solves 2 problems. Very nice, elegant area. This is the area of reinforcement. And we're obviously interested in solutions in here because they'll solve both problems at once. Out here, we have another region of interest. This is a region of conflict. And similarly over here. Both of these are conflict regions. Because solves on one problem, makes it difficult to solve the other one. Supports, obstructs, right? And vice versa over here. Now there's still these 2 center areas are the ones that we would choose solutions from because they're the ones which are positive. So we're still interested in these other 2 regions out here. This one is a plus 0, and that's good because that's a solution which solves or supports resolution of 1 and doesn't have anything to do with the other one. Same thing over here. So what we call these are the regions of independence. And that's true for this one over here too. So what we have are 3 areas of interest. Now what about these other regions out here? Well, you'd never take any solutions from these regions because they're either not going to do anything for you or they're going to cause trouble. And same thing out here. These are no effects. So in terms of our interaction, we're only interested in these 5 regions. And what we can do, if I just pull that out as a little section in here, we've got this little piece and that little piece that goes down. What we see is that the independent parts are ones that are of interest to us, but because they don't really have anything to do with the other problems, they're not involved with interaction. What's involved with interaction is those 3 zones or regions in here where you either have conflict or reinforcement. And the amount of interaction for 2 of our problem elements is, in pretty good intuitive terms, is this set of regions, these 3, against all 5. And that's what we set up as our measure of interaction. We can put real values on this, and we can code it up and set it up as a set of equations, and we can measure the amount of interaction on a basis of 0 to 1, just like we did with similarity, for all the pairings of problem elements using this concept of conflict and reinforcement against all of the, or let's say is really the numerator over the denominator, which includes the conflict, reinforcement, and independence. So that's our basic relation idea. It goes into the relation program, and it's our measures of interaction. I said there are actually 18 measures of interaction. This is one where you have conflict plus reinforcement over essentially conflict plus reinforcement plus independence. But you can see that there are many other possibilities. I could take just conflict. In fact, we do that when we cycle through and go back in and look at a solution that we've already worked on with new information, just interested in conflicts that might arise. So I could have just conflict, or I could have just reinforcement over these. Or I can get involved with all of these other regions. And as a matter of fact, if you figure out all the possible arrangements, we have 18. And that's why I say that there's a lot of potential work that could be done in here and developing new concepts for using these the measure. We really developed it for this particular problem, for working in design. But actually, there are many other things that you can do with it. All right, let's go on from here and talk about the computer structuring that we have to do, and then we'll talk a little bit about synthesis. Computer structuring is done very much like we talked about in the first part of the talk, in that we're going to apply the relation and VTCon programs. It's just now that we know what our elements are, they're problem elements, and we are going to establish the relationships based on this interaction measure. So we'll use the two programs. And the relation part will establish the amount of interaction between each between each, well, I can't say that, for each parent. Let's change that. For each pairing of problem elements. And VTCon then will cluster the problem elements by decomposing a graph, which is made up by relation from this interaction established for all the pairings. And VTCon will then also do the hierarchical analysis. So cluster the problem elements by decomposing a graph and organize the clusters hierarchically. Let's go through the whole procedure here in terms of what we're trying to get at. We start out with research in the general sense. We're collecting information, get the data. Go back to those interviews and the materials that you're going to abstract from, whatever you need. And what comes out of that is data. That's the thing we fill our filing cabinets with. Now the next step is analysis. And here we'll use it specifically to mean turning the data into information. And so what comes out of that is an information base. And that's made up of all these problem elements. The next step then is to do our structuring. And there we use VTCon and relation. The output is an information structure. And at this stage, we're finally then ready to begin what we would call a synthesis stage, where we're going to try to come up with something, but not detail so much as a plan or a concept. So the synthesis stage will produce a plan. And now let's talk about what that synthesis stage is. First of all, we're talking teams. I mentioned that in the beginning, and I don't think there's any real way that you can get around that. The advantage, or one of the big advantages of using techniques like this, is it allows people to work together well in teams. It provides a mechanism for organizing a group activity based on a common methodology or a common information system. So let's look at that synthesis activity now, because now we're really at another kind of teamwork problem. What we need for work in this area is a fairly small team. I mean, if you're working with a really large team for generating information, probably ought to stop at this stage and subdivide it. Maybe work on parts of the problem, or just take one part of the team and let them be the synthesis group. But I would say a team most likely is 3 to 6 people. It's at this stage, that's pretty good. Problem is decision making. The more people you have, the harder it is to make decisions. On the other hand, you need information, or ideas rather, and the more people you have, the more ideas you have. So 3 to 6 seems to work pretty well. Most of the people in group dynamics agree with that. The creativity people feel that that's pretty good. In terms of organization, we do it this way. We have a team leader, and his job is to not really to run things so much as it is to coordinate the activity that's necessary in a group effort. He'll be the one that stands up and works on the vertical surface while the other people are kind of sitting around in a group. He focuses attention, he develops ideas and pushes people to achieve new ideas and keep things rolling along. We have another person we put in, and he's a recorder. It's his job to get it down, because a lot of ideas come and disappear. Now maybe that can be done on tape, but my experience is that you make a lot of tapes and you never really listen to them. It's hard to get that stuff back off the tape. It's probably better to have your recorder getting it down and just picking up the high spots. Maybe you want to listen to a tape too, maybe you do that also, but I still feel that assigning a person on this job is important. The rest of the people are participants. It's their job to come up with ideas, to withhold criticism in the classic brainstorming synectics kind of activity. I would suggest here, as a matter of fact, that George Prince's book is an excellent one to read on the nature of the interactive process that goes on when a team is working to solve problems. It's a practice of creativity, the practice of creativity, I think it is. George Prince is the current president of the synectics group. And this book is in paperback now. It has a lot of interesting things on synectics, but there's a whole chapter in there about how to be creative as a team and what the various group dynamic things are that take place. And since it's organized for our purposes, namely design and invention, it is probably one of the better ones to look at for those activities. All right. Now, what about the procedure? I'll give it to you in a few steps. First, now we've got an information structure. That we produced already using the computer and the VT-Con relation programs. Okay, first step. Select clusters in the structure that you're going to work on. I would say, as just a guideline, probably 5 to 10 problem elements would be good. You don't want to get a lot of them, because then you get into the old problem of trying to deal with too many things at one time. On the other hand, too few of them just kind of waste time. 5 to 10 seems to be a reasonably good number. You don't have to work at the bottom level of the structure. You know, here's a structure, let's say, and you might choose to work here at this level because you've got about 5 or 10 here, but maybe this is 2 or 3 or 4 or so many, and so maybe you come up here and pick up this one, and possibly these are all small too, so you can work here, and then maybe you have to go back down to that level. You can work at different levels in the structure. Now, admittedly, when you go up, you're going to have less coherence. The more you go up the structure, the more you're losing the intactness of those clusters. So you have to kind of be aware of that a little bit, but you can work at different levels. Now here I missed this one, so obviously that wouldn't work. I'd have to pick up that one too. I've got to pick up all of the problem elements. So you got to be careful that you pick a spot in here and then make sure you got all of the branches on down. All right, so that's step one. We find a spot. We select the clusters we're going to look at. These are the ones we're going to address in teamwork one by one. Now, which one do you start with? Okay, that's next point. Two, evaluate the clusters for influence. That's the trick. Influence, remember we brought that up a while back? All right, influence, we're going to do some calculations on here. The average influence for each cluster is going to equal square root of the sum of the squares of the individual influence values. This is for each, in other words, for each problem element, divided by the number of problem elements. Now we can express that a little more compactly if you want to. I equals 1 to n, sum here of all these influence values squared, and divided by n inside the radical sign. Now, the reason you do this is it places more weight on ones which have a higher influence value. Now, let me just show you what I'm talking about. Let's say we had 3 problem elements, and they had 3 different influence values, 1, 2, and 3, and we had another set, and they had the same influence value, 2, 2, and 2. So now what would we have here if we just used a plain old average? Let's say this is cluster 1 now, which had those 3 problem elements, those influences. This is another cluster, those influences. If we use the average, they both come out to be 2. And yet, here we've got one that's very broad in its significance and its influence. So we want to stress that. We want that to come out a little more. So if we use this form here, then what happens? Now we get the sum of the squares here would be 1 plus 4 is 5 plus 9 is 14 divided by 3. So we'd have the square root of 14 thirds, which is equal to square root of 4.7, right? Which is going to be larger than 2. Now, on this one, we'd have the square root of, well, it would turn out to be 2. And so we don't have to worry about that. But you can see what happens is this form gives more weight to the 3, and we get a slightly larger value than 2, and then that will come out to give us what we want, a little more emphasis on those influences which are high over the ones that are low. All right, so that's number 2. Evaluate the clusters for influence. Now we know which ones to start with. We can pick among the various levels and the various clusters at the bottom. Start with the ones with the highest influence. Now let's move on to point number 3. Third thing we've got to do. Develop, design, or planning concepts for the clusters. Now, how you do it is kind of important here. We've tried lots of different ways, and I think that the most successful is to keep it loose, primarily verbally. You can build castles in the air and tear them down, and it's just no trouble at all if you're talking verbally. When you get tight making models and doing sketches and fairly tight drawings, then things get too close too fast. I'll say sketches, but I'm talking about loose sketches here, just ideas to talk to each other with, and diagrams. Again, diagrams are probably better because they are also more abstract. But the key here is loosely avoid over detail. Got plenty of time to get into the detailing. What we want to do here is work on a conceptual level and build a plan first before we go down and start putting all the details in. Next point. Now we've got, let's say we've gone through this now, we've developed ideas for each of these clusters that we've identified. So now, substantiate, modify, extend, or replace. You may have to. Seldom do, but might possibly have to. Ideas going up the structure. All right, so we're moving up the structure. What you'll find in these, if you look at the structure and the output on the program tells you all the linkage, you'll see that most of the links, by far, probably 75, 80, 85%, are down at the lowest level. And as you go up through the structure, the new links that will appear, that will be pulling clusters together, will be few in number. So you aren't going to run into too many things to check out. And that's why we do these lower levels first and then kind of move up after we've developed our ideas pretty well. And you can go through this rather quickly, just checking out, making sure things are okay, or making subtle changes. Finally, write it up. Write up as a plan. Now the plan is really the problem definition for the detail design phase. Maybe I better say that. I'm assuming here, of course, that we're going to go on to a detail phase. It may be that it's an end in itself to finish the planning part. But if you've got to go on further and detail out a process or detail out some physical design, then this plan will become the overall problem statement that you need, and a lot of detail and specification of the problem for the detail designer. I might add, too, that if it's complex enough, you may want to run the computer programs again, and you certainly can. They can do it, and we've done this several times. They run the programs, and for a different purpose here. They run the programs again for a communication structure. You see, communication structure, in other words, the way it organize the plan to communicate to someone, is different from the information structure. What you want to do here is put things together for another purpose. And what I would say here, the relation that you might use would be, is best discussed with. And you could go through and fill out a matrix looking at your various planning elements, or the solution elements, I probably should say, and say yes or no. Would be good to talk about these together in our communication? And if the answer is yes, you mark it, and there's your link. We go back and run the programs on it, and you've got the organization for running a printed piece, or perhaps even putting a slideshow or a television show together. That takes it through. We now have gone through the synthesis, 5 stages that will get you to the end. Let's summarize a little bit and talk about why it's worth doing this. We've kind of leaped into this on a little bit of faith. It's probably worthwhile now to maybe hit on a few reasons for doing this and close off with that. In summary, what we've done is we've dealt with complexity by allowing ourselves to find the elements, combine the elements, and through some kind of linkage means, create a graph as a model, decompose the graph into clusters, and build the clusters back together again using a condensation idea so that we have a hierarchical structure. And then we've been able to use that in the case of design as an information structure, which we can use to give us a program, essentially, for approaching the solution of those problems in the information structure. Why bother with all this? Some of it's fairly self-evident, but I think it's probably worth hitting a few of these, of the good reasons, that, at least as I see it, for doing things like this. First of all, we've got complexity. And that's with us today, and there's no way we're going to get around it. We have more information now to deal with, and more information that should be used, because